Alright, so I'm making a little video to help you with one sample t-test. I'm going to walk you through an example and point out a couple things that you might want to remember about confidence intervals in order to help you with this chapter. So our objective for today is testing a claim about mu. Now previously we learned the tools to test significance in an unrealistic world where we knew sigma, so now we're going to actually practice real life. So here's a little history. It says, what would cause the head brewer of Guinness to not only use statistics, but also invent new statistical methods? The search for better beer, of course. Gossett used experiments and statistics to answer questions like, what are the best varieties of barley and hops for brewing? How should they be grown, dried, and stored? The problem was that when he did these experiments, he did not know the true population standard deviation of his data sets. Therefore, he had to use our sample standard deviation. So we're going to look at one sample t statistics and distributions, and I'm going to try and remind you of a few things we did with confidence intervals. For example, if you take a look here, it says a one sample t statistic. We have our equation for generating our test statistic t. We still have our estimate of x bar minus our mean divided by our standard deviation. Now, when we use our sample standard deviation rather than sigma, we have to deal with something called degrees of freedom. Remember, degrees of freedom is n minus 1, n being your sample size. Now notice our denominator is standard error now. Notice that we have an s instead of sigma, which is why we refer to that as standard error, not standard deviation anymore. Now a little reminder on how to use Table C. Table C can be found in the back of your textbook. Now let's pretend we've started with this problem. We are hypothesizing that mu is equal to 5, and our alternative is that mu is greater than 5. Now assume we already know we have a sample size of 20, and that I just used that previous formula to calculate a test statistic of 1.81. Now notice for this problem, all of this is given to us, so we didn't have to calculate anything. Now, a reminder with Table C is that we need to know our degrees of freedom. In this case, our degrees of freedom is 19, because our sample size was 20 minus 1. Now, notice our test statistic, if I look along this 19 row for my degrees of freedom, my test statistic of 1.81 falls between these two values, 1.729 and 2.093. Now, notice the top of the table has our upper tail probabilities listed. I'm going to use those upper tail probabilities to find my p-value. Now, since my test statistic falls between these two values, that means my p-value is going to fall between these upper tail probabilities of 2.5% and 5%. So the upper tail probability is the p-value of this test. Now notice it was greater than, which is why I can just use the upper tail probability as is. So in conclusion, the p-value is between 2.5% and 5% for this specific problem. Now let me show you what it looks like if it's two-sided. Notice we have the same problem, except we have a two-sided alternative. Our sample size has changed to 37, and we obtained a test statistic of a negative 3.17. Now notice, this being two-sided, Table C only shows the upper tail probability, meaning areas to the right. Now my degrees of freedom in this case is 37 minus 1, which is 36. And notice that 36 is not an available degrees of freedom, so I actually need to use 30. I'm going to go along row 30 until I find my test statistic. Now notice, my test statistic, the positive version, falls between 3.03, and 3.385. Now that's going to help me get my upper tail probability. Now, my upper tail probability is between 0.1% and 0.25%. Now notice, this being just my upper tail probability, to get my two-sided test, I would need to multiply it by 2, making my p-value between 0.2% and 0.5%. Alright, now if you'd like to try this, go ahead and pause the video so that you can try these practice problems. Now when you're doing a one sample t procedure significance test for means, as always remember to follow your inference toolbox. Step 1, I need to identify my population parameters, state my hypothesis, in addition to stating my significance level. Step 2, I need to check my conditions. Step 3, I need to get a shaded picture of my distribution along with stating my test statistic p-value and what test I'm actually doing. And step 4, I need to make my decision and give my context and my reasoning for it. Here's an example that's in your textbook. Diet colas use artificial sweeteners to avoid sugar, but these sweeteners gradually lose their sweetness over time. Manufacturers test new colas for loss of sweetness before marketing them. Trained tasters sip the cola and score them on a sweetness scale of 1 to 10. The cola is then stored for a month at high temperature to imitate the effect of 4 months storage at room temperature. Each taster scores the cola again after storage. Now this is our data. Our data are the differences, the before score minus the after score. Notice that many of these differences are positive and some of them are negative. Now my question is, are these data good evidence that cola lost sweetness in storage? Use a significance level of 5%. Step 1, state my hypotheses and identify my population and parameter. So we ask the question in terms of the average loss. So we're doing before average minus after average, which is our average difference for the population of all tasters. My null hypothesis is that there's no difference, and my alternative is going to be that there is some difference, meaning a positive difference, meaning there is a loss. For my conditions, we'll be willing to treat our 10 tasters as an SRS from the population. Now notice we don't know for sure that they are an SRS. Independence, we need to know that the 10 taste sweetness loss scores can be viewed as independent observations. Note, however, these two scores are scored by the same individual, therefore they are not independent, so we must proceed with caution. And lastly, normality. The assumption that the population distribution is normal cannot effectively be checked with only 10 observations, so we cannot apply the central limit theorem. Therefore, we construct a distribution of our data which appears to be somewhat skewed. We must proceed with caution and recognize that our calculations might not be accurate. Finally, this takes us to our calculations. Our average difference from our scores was 1.02 with a sample standard deviation of 1.196. From this information, I can calculate my test statistic. I have my sample 1.02 minus my hypothesized mean difference, which is 0, divided by my standard error, 1.196 divided square root of 10, because that's my sample size. Therefore, I get a test statistic of 2.7. Now, my sample size is only 10, so you have to ask yourself, what is my degrees of freedom? Well, in this case, my degrees of freedom is 9. Therefore, I'm going to go along my 9 row in table C, looking for my test statistic. My test statistic falls between 2.398 and 2.821. Therefore, my p-value falls between 1 and 2%. Finally, I can come to my conclusion. As a result of my statistical analysis, I have enough evidence to reject my null hypothesis that there is no loss of sweetness in the stored cola because my p-value is statistically significant at my significance level. Notice for my p-value, I put 1.5% because that fell right in the middle of my range, and my test statistics seem to fall right in the middle of the range on table C. Therefore, I have reason to believe that storing this type of cola does in fact cause sweetness level to decrease over time. Alright, hope that helps in terms of one sample T procedures. Remember, you're more than welcome to go back, watch this again, and pause at any points if you'd like to practice.